We're going to finish up what we've been talking about, the first law of thermodynamics. So the very last section we have to talk about is delta H's for chemical change. Camera set up. Okay, so this is very, very similar to physical change. So, and it's very similar to things you did in Chem 107. So the plan will be, I want you to read this topic really carefully. And as you read it, record in your notes the definition of all terms that are in bold, put in all equations and explain what they're used for, and then do all the worked out self-tests. We'll probably take class time to do this, but I'll see where we're at and what other things we're doing as we finish up this focus, but probably we'll do that in class time. The only thing I want to talk about is the very last section, because it's a new idea and you won't have seen it before, and that is, how does a reaction enthalpy change with temperature? So in Gen Chem, we just assumed that a delta H was the same even if we got it out of the table and we were carrying out the reaction at a slightly different temperature. But if that's not the case, Kirchhoff's law, which is given in a general form, and I just want to go through an example so you can see where the equation comes from. So how do enthalpy changes change with temperature? So this is self-test 2F.6, and it asks you to determine the delta H of formation for ammonia gas. And so at a different temperature than would be in the table, so at 400 degrees. So it's a really common thing to need to do, which is, we know Hess's law is true. So if I want the delta H for this reaction at 400 degrees, I just need to figure out, how do I change the reactants into the products in another path, and that those steps have delta H's I can understand. So the first step I'm going to put here is taking the reactants and cooling them off. So going from 400 to 298. And then I know in my table I have a delta H of formation for ammonia at 298. And then in order to get to the product at 400, I'd have to just heat that product back up. So, those are my steps. I have a path that's equal to the reaction I'm interested in at the temperature I'm interested in, and the path involves first cooling off reactants, then carrying out the reaction at a temperature I know the value for delta H, and then heating the products up. So from what I know about enthalpy, I know that this is true. And so if I change the temperature, how does enthalpy change? So I can do this. And then I can integrate both sides. And if Cp is constant, then I get Cp delta T equals delta H. So that would mean for these steps of cooling and heating, all I need to do is multiply the heat capacities by the temperature difference. So for step 1, that would mean I need the heat capacities for hydrogen and nitrogen. I need to multiply them by the number of moles in the reaction, so 3/2 for the hydrogen, 1/2 for nitrogen. And then I need to multiply both of those by 298.15 minus 400, because in this step, 298.15 is T2 and 400 is T1. Then I need to add to that the delta H of formation at the temperature I have it in the table. And in the table, it is negative 46.1, and that's in kilojoules per mole. And then I put in the first set of units for heat capacity. These are in joules per kmol, so I'm just going to have to make sure that each of these terms is either joules or kilojoules. The heat capacity then for the heating up the product side is 35.06. There's 1 mole of it. And for that step, T2 is 400 and T1 is 298 because I'm heating those up. So when I put those values in, each of the terms with heat capacities, I have to multiply to get into kilojoules, so I can add to this kilojoules. And so this cooling of reactants added to this delta H of formation, added to the heating of the products, gives me the delta H of formation at 400 Kelvin for NH3. So there's a generalized expression for this that looks at the difference in heat capacities of reactants and products. And then notice this delta T is just reversed. So I could have the delta T the same, but change the sign. So when you look at that generalized expression, that's all it's doing is taking this idea that you look for a cycle. And if you can add these 3 steps together and get the same overall process, then you'll know what the delta H is at that new temperature. So that is it for the first law. We'll move into the second law and get very close to understanding equilibrium.